That don't really understand the movement of moisture and how it affects the building envelope and the control layers that we implement to manage it. So we started out just looking at water as a molecule, and then we'll expand out to talk about control layers. I spent a lot of time finding and remediating moisture problems in existing buildings, often older buildings or rehabbing buildings, turning them into new things. Moisture and mold and leaks, they're always present in these older buildings because we didn't understand control layers as well as we do today. My pro tip for you today is that preventing problems in new buildings is going to be much easier than fixing them later. Who is MEADOWS? MEADOWS is a 100-year-old company. We are all American manufacturing, 13 facilities throughout North America. An example of a few of our many offerings, we have over 350 different SKUs in our catalog. Here are our learning objectives. We are going to understand the effects of moisture. We're going to understand the basic science of how it behaves as a solid, liquid, and vapor state. We're going to identify and differentiate between the different control layers that we can include. Some of those we'll be able to make multiple control layers in one product. And we are also going to consider key details for the prevention of moisture movement. Little spoiler alert, details are really going to matter. Details, probably the most important thing we can talk about. And then we're going to talk about some best practices. So let's get started. I get questioned, why build buildings that don't leak? And one thing we need to understand, number one thing is that air leakage is the largest source of energy loss in most buildings. Air leakage and air exchange. If you can control the air exchange and manage that correctly, that is a massive savings of energy, which drives occupant comfort, which is in high demand right now. If you have a building that leaks, you cannot have superior indoor air quality because you're getting pollutants coming in and out through the envelope. All of this, a tight building has a much lower environmental impact. The HVAC system on a building that has a superior air barrier can be reduced up to 30%. There's a significant environmental impact that you can have by making a building that manages air and moisture. And all of that gives us a high performance, sustainable design, which is what the market is looking for right now. A few facts about moisture management. It's still the biggest cause of post-construction lawsuits. Look at the date above the ASTM symbol there. That was a 1982 study. It's 2026, but we're still seeing moisture and water intrusion as the biggest cause of post-construction lawsuits. And there's that EPA-based study. That also hasn't moved a lot since that was put forth. We are still building a lot of buildings that leak and a lot of buildings that have a resultant moisture management problem. So let's talk about mold, because that's what usually gets us called in. Mold growth, bad air quality. There are three things that we need for mold growth. We need food, we need mold, spores, and water. Any organic material is going to be mold food. That's wood, paper, pollen, dirt, anything that's organic can be mold food. You'll find mold spores even in Antarctica. So they're across the entire globe. The only effective way to manage mold is to limit the availability of moisture to that mold. And you can always see a mold growth is going to occur at the windows, at the places where the water is going to condensate, because that's where it has the most available moisture. So if we can manage the moisture, we will not have mold as a problem. We get a lot of structural damage from water. Concrete, water brings a lot of deteriorating agents into the concrete. Chlorides, salts, acids from soils or strong alkalis, causing deterioration of the concrete. It expands and it freezes, causing spalling. It affects the rust jacking. It'll rust steel. And there's a fantastic slide in the middle taken by a friend of mine in the New York City subway system exhibiting rust jacking on a structural connection. You can see how the water gets in and combines with the iron, adding extra oxygens, expanding the material and causing it to exfoliate. And the slide on the right, the wood, happens to be the last house I occupied in New York State. Somebody saved $30 worth of flashing, and that was the result of the deck, or how the deck connected onto the building. So managing moisture in any structural system is an important thing to retain structural integrity of that system. When we talk about how water moves the same way inside as it does outside. it evaporates. It goes from a high concentration in a liquid state to a more dispersed concentration as a vapor. And then it tries to lose energy, bring it back together and condensing itself and precipitating out. The water cycle happens the same inside the building as it does outside. There is no magic mover of water that science can't explain. Vapor drives, all of these things are all very scientific and very predictable once you understand the science. And it all starts right here. So water is a polar molecule, and if it didn't have the hydrogens sticking off the sides, it would not be a polar molecule. But because the hydrogens have a slightly positive charge on one side of the molecule, and the oxygen has a slightly negative charge, you end up with these hydrogen bonds, which allow this incredibly lighter than air molecule to clump up rapidly, and as it loses energy and return to its liquid form. So as you can see on this slide, O2, which is an air molecule, and N2, which is a standard air molecule, both those make up most of our atmosphere. They have an atomic weight of 32 and 28 respectively. Water has an atomic weight as a molecule, as an individual molecule, of only 18. It's much smaller than either one of those. So when you look at a vapor permeable air barrier, this is how we are able to make a water vapor permeable thing that stops bulk water and bulk air. The water molecule is actually smaller, so we can control the length of the polymer chains when we're formulating these things, or the network of fibers, to the point where you can allow a water molecule to escape, but still resist the penetration of air. It's still too small for air or water droplets to come in. The hydrogen bonds again cause the phases of water to act differently. Water as a solid expands, and that is because these hydrogen bonds cause this hexagonal structure. Something very important to understand in the northern climates is that those ice can exert tremendous pressures, even lifting manholes and building foundation elements up out of the ground if they're not addressed correctly. Water is at its densest as a liquid, and then as steam, it tremendously expands. So when we talk about water vapor, we're always going to be talking about water as a gas, as an individual molecule in its gaseous state. And there's tremendous energy phase changes here that happen, and that is because of those hydrogen bonds needing to be broken. When we look at evaporation, it's always happening. Anytime you have the presence of liquid water and air that is not at 100% relative humidity, you are going to be having evaporation. And the actual water vapor is invisible. What you see on the surface of that lake there are water droplets. So the water, individual molecules of water have achieved enough energy to escape off the surface of that lake and then immediately bumped into another one and clumped up into droplet layer. But the evaporation is still continuing, it's still going up, and so that mist is dissipating into water vapor that you can't see. And why all this matters is that water vapor is the most important mechanism of drying. And when you have air movement, if the wind would blow over that lake, you'd have a lot more evaporation because you're moving fresh, dry air over the lake, which is sucking up more water molecules off of the surface. Has anybody ever done a heating calculation on an app or online or in a program? If you have, you'll notice that you're always asked how many occupants there are and how many plants. Why? Because people and plants are also a source of water. So not all water in our building is coming from outside the envelope. This is why we need controlled air exchange. Condensation, anybody who did building science or architecture, you probably took a class, comfort, climate, and energy class possibly, where you had to draw one of these temperature gradients going through the wall, where you're starting out at 0, and then the temperature gradient is going to go up to 70 degrees inside temperature. And somewhere you're going to look on the psychrometric curve, you're going to find that dew point, which is going to cause the water to drop out. Yes, it is true. The dew point is going to happen there. The water is going to condensate out there, but it is going to continually try and keep losing energy. So it's always going to go to the coldest surface that it can't pass and collect on that. So that is why you have water that condensates out on glass, on the exterior sheathing of a building, around the windows. Water is always going to be collecting on the coldest surface. Hydrostatic head is an important concept to understand. In the slide there, you can see a block foundation that has a blindside waterproofing on it. That is because there's some hydrostatic head that is going to be present on the site. Basically, hydrostatic head says the deeper the building is in the water, the greater the pressure of the water trying to get into the building. It can be calculated. This is important, especially when we do negative side waterproofing. When we do negative side waterproofing, it's very important that whatever waterproofing material we put on the negative side, that bond strength exceeds the hydrostatic pressure pushing through the wall. So it's all hydrostatic pressure, hydrostatic head is all about the depth of the water column. Capillarity, this is another property that results directly from water being a polar molecule. As a polar molecule, water will adhere to certain materials better than it does to itself. And when you have a small gap, water is able to do that even more, and it can rise against gravity. The smaller the diameter, the greater the rise. One very important takeaway from this slide is that to break capillary action in water, we need a gap of 1/4 to 3/8 of an inch. That is why when you design a rain screen, those gaps are 1/4 to 3/8 of an inch in between the rain screen cladding. That is why when you put a drainage mat on the outside of a building, that drainage mat is at least 3/8 of an inch deep. It's all to break capillarity. So if you want to draw a break on capillarity, you need a gap of 1/4 to 3/8 of an inch. Percolation and absorption are important concepts to understand. When we talk about permeability, we're talking about the ability for a fluid to flow through the material. When we're talking about porosity, we're talking about the volume of voids in that material. So you can have a very low permeable but highly porous material like closed-celled spray foam, and you can have the vice versa of that, which would be an engineered vapor permeable air barrier. Here's a slide that shows the psychrometric curve, and it's all about air transport. And what you can see here is as the dry bulb temperature increases, the ability of water to be held in that air goes up. And if you look at the chart around the 60 and 70 degree mark on the enthalpy scale, that's where it starts to steepen out. And that is why we have room temperature set where it is. If you have a client that wants to set their room temperature back at night, they need to manage their moisture content, their relative humidity, even more so in the building than you would if you kept it to a constant temperature. You can end up with a lot of condensation problems in a building once you start cooling it down in the 50s for a nighttime setback, and I have seen a lot of that kind of problem in my work. So water is always going to try and disperse from a more concentrated state to a less concentrated state, right? It's the law of entropy. So if you look at this as water molecules on the surface of the lake, the average temperature of that lake surface represented by the thick amount of molecules there may be 50 degrees. It may be 40 degrees. You're still getting water moving off of it because those individual molecules may be at a higher energy state, or they would be at a higher energy state than the average. Temperature is always an average of energy, but each individual molecule can have a widely varying amount of energy to it. So water is always going to move from a more concentrated state to a more distributed state. And then water is also always going to try and lose energy once it is in that distributed state, and then it will concentrate again. So let's talk about the water impacts to envelope design. Liquid water enters from above grade and below grade. We have water vapor entering above and below grade. We have water from living things enclosed by the envelope, and we have water from processes enclosed by the envelope. So here's some slides about liquid water. Here's one hydrostatic pressure pushing water through a failed footing drain in through a crack in a building. That was fixed with a negative side waterproofing of a cementitious coating. You have water entering through cracks and pinholes in deteriorated roofing, often moving through capillary action through the various layers of that roofing and then leaking into the building through another gap or crack. Here we have on the right plumbers. Plumbers are a fantastic source of water in the building, both intentional and unintentional. That one there is a hose bib that had a leak and water would also condensate out on it in the morning dew and the evening dew, and then run in through that gap there. And it was a finished basement, and it caused a nice bit of mold growth right behind there. Once we found that, we sealed up that joint, and no more problem, no more mold growth. Capillarity will always draw in through small gaps. Windows and window trim are a notorious thing. Here you see a non-traditional way of running the subsill past the jamb trim there. If you look at an older building built by a traditional carpenter, that side trim will always come past. And there will always be enough gap there so you're not having a capillary break, or it's always sealed with paint or some sort of caulking or sealant. Another way that we have capillary action bringing water into the building is through the footing. If you look at where the footing drain lies, the perforated pipe, it's always a little bit up from the bottom of the footing, which means that that footing can be sitting in water. If it is, you're going to have capillary action pulling water in up through the concrete and up into the concrete stem wall and the slab, and it can bypass the polyethylene vapor barrier that you put subslab. In Europe, in most instances, they demand at very least an asphaltic emulsion to cover the top of that footing as a damp proofing and a capillary to stop capillary action from bringing water into the building. It's coming into our code. Some jurisdictions are allowing it, some don't. But the trend is we're going to see pretty soon the tops of footings needing to be damp proofed. Capillary action also happens in steel roofing and flashing. You can see on the far right how water comes as a drop, works its way around. That is why we put that extra sealant in the joint. And yeah, it means that water sneaks into the building in ways that you would think it didn't. Back when Joe Stiebrick and the Building Science Corporation people were figuring out the basis for air barriers and air permeance and vapor permeance, they started out with a 4x8 sheet of gypsum board. And they tested it under laboratory conditions. They put a vapor drive on it just to see how much vapor diffusion they would get through a 4x8 sheet of gypsum board. And they ended up with 1/3 of a quart of water. And for fun, they cut a 1x1 hole in that gypsum wallboard and end up with 30 quarts of water. So you can see how much water air transport can result in. Vapor diffusion is going to be relatively small, but once you have an air leak and you're subjected to an air pressure differential, you can move an awful lot of water through a very small hole. So here's a slide about vapor drive. This is a wood manufacturing plant that had humidification in it, and water was 50% relative humidity. And we had a vapor retarder on the ceiling there, a vinyl-faced insulation. It was not 100% sealed or effective, so the water vapor got up there, condensated out onto the bottom side of the steel, and then rained back down, causing those panels to sag and leak. The owner thought the roof was leaking. The roof was not leaking. We inspected the roof. It was actually a condensation issue. The way we solved that one was we added continuous insulation over top of the roof deck and single ply membrane on top of that to keep that steel warm, no more condensation, no more leakage. If you ever pull a wall apart, you see fibrous insulation. That black stuff there is kind of a telltale of where the air and water have been moving through the insulation. And it's always where you'd expect it, predictable. Down at the bottom where it's not sealed very well, and along the studs where you have a lot of penetrations of screws and other things, allowing moisture and air to get through. So let's talk some practical application about control layers. We're going to manage moisture with control layers. Above grade, we're going to use vapor retarders to control water vapor. We're going to control the air transport of water using air barriers. For thermal control, we're going to use insulation. And insulation was brought into the building code to condensation. And if you think about that for a little bit, that is the greatest argument that anyone can make for continuous insulation. Liquid water is also going to be above grade, and we're going to control that with roofing, cladding, and weather resistive barriers. And below grade, liquid water, we will control that with waterproofing. And we are going to do some thermal control with insulation, and we are going to have to control water vapor. When you hit 55 degrees in ground temperature, you are across the globe going to find 100% relative humidity. So below grade, we need damp proofing and vapor retarders. So when do we need these things? Sometimes you need vapor retarders above grade, but you're always going to need to stop the air transport of water. Why? Because that's your biggest energy loss and it's your largest source of water. We're always going to need a thermal control insulation layer to control condensation. We're always going to require some sort of protection from liquid water above grade. Below grade, sometimes you're going to need waterproofing. You don't always need waterproofing, but you're always going to need thermal control for insulation to prevent condensation on the inside of the building. And you're always going to need some sort of water vapor control. That is because when, like I said, 55 degrees, when you dig down to 55 degrees, you're always going to have 100% relative humidity. You always have a vapor drive coming from the ground. And that's also why ACI now requires the use of vapor retarders sub-slab. So let's talk a bit about vapor retarders. Class 1 vapor retarders, we're talking about polyethylene films, sheet metal, glass, foil-based sheathing. Class 2 low permeance, those would be craft paper, unfaced expanded polystyrene, and some paints. Class 3, that was set to the gypsum board, latex paint, cellulose insulation, house wrap. Those are all medium permeance. The important thing to remember here is that you are allowed one Class 1 vapor retarder per wall, floor, or ceiling or roofing assembly. You're allowed one. It has to be in one place. If you have multiple materials that are Class 1 vapor retarders, the best practice is to try and group them together. We have three kinds of vapor retarders to choose from. We have the plastic type, which is the most common, and we have asphaltic type. That was actually the original subslab vapor retarder, was an asphaltic board brought forth in the late 1940s. It has extremely low permeance, averaging 10 times an order of magnitude of less permeance for water vapor than the plastic. And the plastic is pretty non-permeable. And then we have the smart vapor retarders. Those are the oldest and newest category. They're the polyamide films. They're also craft paper and wood, which both work very similarly. So it's important to understand that vapor pressure is a distributed load. When we're talking about vapor pressure, we're talking about the presence of water vapor, and it's attempting to distribute itself out and even its presence out in the environment. So that's where vapor pressure will come from. Water trying to equalize. And so you can have a 5% compromised vapor retarder. It would still be 95% effective if all you're dealing with is the distributed load of vapor pressure. But if a vapor retarder is subjected to air pressure differentials, it must also act as an air barrier. This is why we try and couple the air barrier with the vapor retarding layer if we need a vapor retarding layer. So vapor non-permeable air barrier includes the vapor barrier in the air barrier. Why? Because they both need to be together. And once it becomes subject to air pressure differentials, it needs to be 100% continuous. If a subslab vapor retarder is subjected to liquid water, it also must act as waterproofing, even temporary dynamic waterproofing. So there you have it. Most vapor retarders will fail when they are required to do more than be just a vapor retarder. So when we're talking about a vapor retarder, typically we're talking about things that we're trying to have them subjected only to the distributed load of vapor pressure. Once you have the air pressure differential, which you can even get on a subslab condition, if you put the building under negative pressure, you can still have a negative pressure differential applied to that. Those need to be really continuous. And that's the argument for continuity. Here we have a slide that talks about smart vapor retarders and shows how they work. And just the cellulose-based and the polyamides, when they're subject to a higher level of humidity, those structures open up to allow water vapor to pass through. Subslab vapor retarders. The most common, ASTM 1745. The oldest and least common, but also the most durable and still has niche application, the ASTM 1993. Those should not be in the same spec section. They need to be in separate spec sections. They are different materials. I still see them mixed up, but primarily when we're speccing subslab vapor retarders, we should be in the ASTM E1745 section. And that should also include a section on the need for the accessory tapes and detailing pipes and penetrations. When we're talking about air barriers, I teach a whole class on air barriers, should they be permeable and non-permeable, and another one on the detailing of air barriers. There's a lot to know about air barriers. Right now, for this presentation, we make it super simple. If you are in the white area of the country, you need a vapor non-permeable air barrier. If you're in the gray part of the country, also known as weather paradise, you are allowed to have a vapor permeable air barrier. What drives permeability versus non-permeability has to do with temperature gradient. If you have a high temperature gradient, you tend to need vapor non-permeable air barrier. So that's all we're going to talk about air barrier permeance versus non-permeance. But the material choice is determined by fire code requirements. And this is why there's also fluid applied versus sheet applied. Fluid applied is better for some geometries. Sheet applied is much easier on large flat surfaces. when it comes into selecting an air barrier, there's always going to be a broad portfolio to look through from each manufacturer. And it's just important to consider all the things that are going on your project. The geometry, how many penetrations there are. There's a lot of penetrations, you might need a fluid applied. So those are all things to consider about air barriers. Which one of these materials is not an air barrier? Fact is, they're all air barriers. They're not all good air barriers. Peanut butter is an air barrier. It passes the ASTM test for blocking bulk air. Sheetrock blocks bulk air. Masonry, concrete masonry blocks bulk air. Precast concrete and site cast concrete both block bulk air. Concrete, masonry, sheetrock, all those rigid materials are great air barriers until they're not. And what do I mean by that? Well, what does concrete or concrete masonry do? It shrinks, it cracks. What does sheetrock do? It shrinks, it cracks. People cut holes in it to put outlet boxes in, extra switches. All of a sudden, it's not an air barrier anymore. So what are we looking for? What makes a good air barrier? First of all, it's got to meet all the references in the code, and it's got to meet all the ASTM tests. ASTM 2357, the leakage rate of assemblies is a more important standard to meet than ASTM 2178, which is just simply the air permeance of the material. We also test these things as assemblies, and there's a standard means for doing that. And you can see material and air barrier material, sheet applied, being put onto something that's subjecting it to an air pressure differential. And the lab is going to see how much air they can draw through under pressure. So a good air barrier is going to be durable. It's going to be flexible and resilient because buildings move, materials move. It's going to have great adhesion to the substrate. In my opinion, an air barrier needs to be fully adhered to the substrate. Things that can pop loose, a small tear or rip can result into an awful lot of air movement. It's got to be UV stable. And here's where you get into different types of air barriers. Some have limited UV stability to 6 months, some infinite UV stability, some only a year. It's important to know that it affects the price point at which that material is brought to market. If you have long delays or anticipated delays, you want a more, in your cladding package, a more UV stable air barrier. A good air barrier also is going to be your weather resistive barrier. You shouldn't need a weather resistive barrier that you add onto the building, an air barrier that you add onto the building. We're going to combine these things. And in some climates, we're also going to make that a vapor retarder. So you're going to get 3 in 1 with a good air barrier. The other thing is compatibility. That's the other thing that you're going to think about when you're selecting an air barrier. How compatible is it with the other sealants that we're using on the building? How easy is it to install? Does it need special detailing, or can we stick the waterproofing membrane right onto it, or stick it right onto the waterproofing membrane coming up from the foundation? Can we run the roofing membrane directly onto the air barrier? Does that need special detailing? All of these things, they can drive different chemistries and different formulations of air barriers. When we talk about waterproofing, there's 2 major categories in waterproofing. There is hydrostatic waterproofing, which we use below grade when water is going to be put on the waterproofing. You can almost imagine it as a dead load. We're going to make that waterproofing, if it's hydrostatic, so they can take water as a dead load. It's going to always be able to resist water. It's just going to assume that water is always going to be there and it's going to resist water. Hydrostatic waterproofing is typically tested down to 200 and some feet of hydrostatic head. The material there is definitely one of those. It often requires a multi-component system. What you have there is a primer, a sheet applied membrane. It's lapped down onto the footing, which is a joint that is treated before it's rolled, before you roll that membrane out. They've put a cove, a 3/4 to an inch cove of building mastic or material back there to seal the joint between the foundation wall and the footing. Then they've lapped that sheet applied over that. And at the end of all of that, they put a termination sealant on the end of that sheet applied membrane so that no water can wick in. So hydrostatic waterproofing is always multi-component. It always has some complexity. It always has a lot of belt and suspenders. Hydrodynamic waterproofing, typically looking at things that shed water, treat water as a live load. So your roofing membranes, your sidings, all of those things, that's hydrodynamic waterproofing. And why would you make that hydrodynamic versus hydrostatic? Well, we're already optimizing the roofing for UV resistance. That's not a concern when you're burying it below ground. You're optimizing the roofing membranes also for economy, being able to be affordable. The two are very different. Do not use roofing membranes in a split slab assembly. That's not what it's meant for. Do not use in a plaza deck or anything like that. You're going to want to use something that is a hydrostatic waterproofing in a planter. All of those things where water is going to be treated as a dead load, you're going to want to use a hydrostatic waterproofing. Damp proofing. Damp proofing is great. It's really, really cheap. You don't always need waterproofing. And when you don't waterproofing, because of the relative humidity that is constantly in the soil, you are going to want to use damp proofing. Damp proofing is typically an asphaltic emulsion. It is a below grade only material. It prevents water vapor intrusion. It does not bridge cracks. Damp proofing is a light duty coating that just stops the passage of water vapor. And you should not use damp proofing if there's a chance of liquid water pushing against the assembly. So if you have irrigation system or a garden nearby the foundation wall, you are going to want to move up to waterproofing there. If you don't have that, if you don't have water table issues, use damp proofing. You'll save yourself some money because it is the inexpensive option. Conventional waterproofing, we have two means of doing conventional waterproofing. We're always going to go for positive side waterproofing if we can, and that is to put the waterproof coating on the side that's receiving the water. So we're going to keep the concrete dry. We have a lot of options for that. Negative side waterproofing systems, that's when we can't get at the wet side. Maybe we're doing an adaptive reuse. Maybe we're coming into a basement that developed a leak somehow and we need to fix it. And we have some specialized coatings going to be applied to the inside there that stop the water from flowing through. So for positive waterproofing systems, we're going to use sheet waterproofing membranes, fluid applied membranes. We can use flexible cementitious coatings, and those coatings are always going to use protection boards and composite drainage boards to protect the membrane from the backfill. When we're talking about negative side waterproofing systems, our options are more limited. They are always going to be crystalline waterproofing, which can be applied as a slurry coat, or flexible cementitious coatings. Both of those are water vapor permeable, and it's important for those negative side systems to be water vapor permeable because the water vapor can develop enough pressure to debond a non-permeable coating, and it will eventually debond any non-vapor permeable coating that you apply there. So that's why we use a vapor permeable on the negative side. We sometimes do blindside waterproofing. So if you're at a zero lot line, or if you're at a place where excavation is steep or impractical, you're going to use a shoring structure, like a wood shoring structure or metal piles or something like that to retain the soil. Then you can put a protection board directly on that. That's the black on the slide. And then you can roll out a waterproofing membrane there and then put your bar, cage, and everything in there and your inside forming, and you can cast concrete right up to that. And you have your waterproofing installed. It's installed in reverse. It's important that the shingle laps also be in reverse so that they are lapping out on the wet side. It's important that it's detailed correctly. Most of these membranes have a fleece backing that mechanically adheres to concrete. Some of them have an adhesive material that activates by the concrete as it hydrates. And some manufacturers couldn't decide which one to do, so they said, do both. But you'll see it. It's an excellent way to waterproof a building where you have difficulty excavating. It's also an excellent choice if you are putting an elevator pit in a historic building that didn't have one before, or putting an elevator pit in where it wasn't before. It can minimize your excavation and your slab cuts. Crystalline waterproofing is an interesting thing. Crystalline waterproofing, we're growing crystals of calcium silicate hydrate in the pores of the concrete. So we're adding extra calcium silicate hydrate to the concrete. If we're adding it as an admix, that would be your crystalline admixes. Cementitious works the same way, where it grows those calcium silicate hydrates. It takes time for these crystals to form. It takes up to 28 days for these to form. So it's not going to be waterproof right away, but as an admix, you can have 99% water impermeance in a slab, and it's very impressive, very useful in certain situations. But it does take time for these things to form. It becomes integral with the slab. And the other wonderful thing about making it integral into the as an admix to the concrete is that you're going to have self-healing properties, because there's always going to be some unreacted calcium silicate hydrate in there that will bridge over and cause new crystals to form if there's a hairline crack and water intrusion. Cementitious waterproofing is often applied as a slurry coat or a very light porridge coat. It does require a fabric embedment for changing planes and going over cracks. Very, very useful. It has a polymer modification to it, and it remains very flexible. Excellent way to waterproof things. Very simple and easy to apply. So now we're getting to the detail portion that I told you about. Details matter. The wall to roof connection is one of the most failed details in building science. And why is that? Mostly because of sequencing. Sequencing where the contractor is going to roll that roof membrane out, and then maybe we'll apply the air barrier after we have the walls infilled or any of these things. But those two need to connect. Somehow that air barrier needs to connect up. Waterproofing and air barriers must have full continuity to be effective. So at some point, you need to be able to run a red pen around the entire building in any given section and have it not lift off of the continuous air barrier or air control layer. There's a number of ways to do it. You can use the roofing membrane as your air control layer, and that would mean that you'd have to bring that down and connect the air barrier up to it on that blocking underneath coping flashing there. You can also bring it onto the top of the roof deck underneath the insulation. It can be done with spray foam. There's a number of ways to do that. The important thing is to take some time at that connection and detail it out. Make sure that the materials are compatible. If the materials are incompatible, you might need a transition membrane. You might need a transition flashing there. And you're thinking in 3D, right? So you're thinking in all three dimensions, do we have continuity? Not just one, but if you have a metal flashing to separate chemistries, you're also going to have those end seals on that. The failure of a joint or penetration can equate total system failure in waterproofing and air barriers. So these joints where the two systems meet up, the penetrations where we're going to put window insulated glazing units through, those need to be detailed carefully. And you need to put some thought into those and take some time. And once you have a good detail, just keep it in that CAD library and you will save yourself a lot of time and money and an awful lot of failures. Details matter. Again, penetrations, pipe penetrations. The upper penetration has a finger flashing on it and is covered up with another piece of membrane and then a building envelope mastic. We put the finger flashing on there to connect it up to the membrane behind it to distribute stress. There's a lot of stress that can be placed on a pipe. It might move differentially from the actual building. The plumber might come and have to wrestle with that pipe to try and connect up a new system to it. If it doesn't have a robust connection that can distribute those forces back out onto the membrane and stay as a system, you can have a potential point of failure there. So 99%, 1% principle, 99% of the leaks are going to come from 1% of the total surface area of the building. Those are going to be pipe penetrations, other penetrations, and transitions. The second 99% principle is that 99% of the leaks are going to be attributable to causes other than material or system failures. And that is why we are going to always try and detail these things out with belt and suspenders. Here you can see a standard pipe penetration detail, a lot of detail in there, a lot of extra things, backer rod sealant, a finger flashing, an additional termination sealant, and then drainage mat over top of that. Fixing these leaks is extremely expensive. Doing them correctly looks very, very economical once you have to fix one or two. Excavating a pipe penetration to try and waterproof it after the fact is difficult. This is one of my favorite slides because it puts it all back on us in the AEC community. We own all of these things that influence product effectiveness. We own the design, we own the geometry, we own the selection of materials, we own the workmanship. Workmanship can be specified. You can specify a qualified installer. Quality assurance, you can specify testing, you can specify manufacturer representative to come out and make observations of the install. You can specify third-party inspections. So all of these things can be specified. They're all in our wheelhouse and we need to take control of those so that we can stop having leaky buildings that causes construction litigation. So to summarize, hopefully we now understand the way water moves, and hopefully you can have some ability to make scientific decisions about the envelope. Quality materials are always going to be designed and tested according to these scientific principles. Workmanship matters. You need to use trained applicators. You need to detail things out carefully. The craftsmanship of your drawings and your specification really has a large impact on the success of any project. And quality assurance. Let's get those site observations on critical phases and details. Let's get some detailed checks before the thing goes out to bid. Let's just pay attention to what we're doing, and we wish you lots of success. Thank you, everybody. Have a wonderful rest of your day.